we are in the middle of showing the boundedness of the Hilbert transform on H1 Hardy space. And so in the sort of grander scheme of things, this is really showing sort of like the power of the atomic decomposition, right? Like showing that you know, it's really nice to have H1. It's really nice to have an atomic decomposition of H1, because then to prove things, you just need to prove it on atoms, and then you can go from the result on atoms. Then you can go from there. Now, like I said, this is sort of historically backwards, because H1 was first defined in a completely different sense, and then normally you define H1 in a completely different sense, different way, and then you realize that it has an atomic decomposition. And so, Stein in his book, and this is the wrong book, Stein in his book calls this applications of the atomic decomposition. But it's strange to think, since we've defined H1 in terms of the atomic decomposition, it's sort of strange to call it an application of a definition. Anyway, so what we're going to do today is finish up that, and then we will give an alternate characterization of H1 using maximal functions. And then from there, we'll talk about the dual space, the dual to H1, which is so-called BMO, the functions of bounded mean oscillation. Right, and all of these things will sort of be simplified by using the atomic decomposition. Okay, so it's really like this last part of it is showing, this last part of the chapter is really showing the power of the atomic decomposition. Sorry. There's a joke involving functions of bounded mean oscillation, but it's actually a crude joke, so I'm going to avoid telling it. This joke was told me by an analyst years ago. Okay, so we were in the middle of showing this theorem that if you have some function in H1 and you have then it turns out the truncated Hilbert transform applied to that function is in L1 for all epsilon. Right? And in fact, so what we had shown that for an atom, H epsilon A in L1 norm was bounded by some constant. Okay, and this was uniform for all epsilon and for all A's. Okay. So that's the first part. Each of these guys is in L1, and 2, these guys converge in L1 to something which we call H of F. Okay, and we'll say that HF in L1 norm will be bounded by some constant times the H1 norm of F. Okay. So that's the theorem that we're in the midst of proving, and like I said, what we showed before was that if you have an atom and you apply the truncated Hilbert transform to it, then its L1 norm is bounded by some constant. You remember how we did this? We used the L2 boundedness right? We use the L2 boundedness of the transform to control the integral locally, right? We divided the integral into sort of local part and global part. The local part we controlled using the L2 boundedness of the operator, and the global part we controlled using the smoothness of the kernel, Okay. Okay. So, and you also recall that we observed in the course of this. So we had shown this. We'd also observed that that all of these guys satisfy a certain decay, right? For x bigger than 2 or something like that, right? That they all decayed, and that this constant was independent of epsilon. Okay, so that's where we were. Okay. So am I right? Okay. So let's continue the proof. Right. So we have this result that for an atom, all of the H epsilons, L1 norms applied to that the L1 norm of H1, the H epsilon A is bounded by some constant. Okay. So now recall that the HEA converge to, we showed earlier that these guys actually converge in L2. Right? These guys converge to the Hilbert transform in L2. Right? Okay. So, and we also have this fact that at the same time, we have the fact that these guys satisfy this decay condition for x. Right? These guys satisfy this decay condition. And I'm going to say that because of that, A and B imply that these guys converge in L1. That these guys converge in L1. Okay. So it's certainly not true that if you have convergence in L2, then you have convergence in L1. Right? That's false. Right? But what happens if you have an additional decay condition? Does that give you convergence in L1? Yes, it does. Yes, it does. But I'd like you to think about it. So just for exercise, mental exercise, I'd like you to think about this for a minute. Maybe the first thing to think about is suppose this thing is compactly supported. Suppose it doesn't just decay; it vanishes after a certain outside of some ball. Okay. So just think about it for a minute and see if you can come up with some rough argument of why we actually get convergence in L1. Okay. Do you want to talk to each other? Fine. I'll give you another minute. You guys talk to each other. Talk to each other. It's good practice. If you're going to graduate school, you have to learn to talk to each other. I spent most of my graduate school not talking to people. In fact, I spent all of my graduate school not talking to people. So it's a good talent to be able to talk to people. Talk to each other.
So, you have this decay condition, but the decay condition itself is a one interval. So, my intuition is that when x is small, the sort of blowups that cause you problems in L1 are always going to are always going to be less bad when you square them first. I'm not really sure what I mean by that.
Yeah, if you're, well, you said that, yeah, that rewrite.
Mm-hmm.
But if you're,
Yeah. So what do you think? What do you think? What do you think what kind of tool should we use? What kind of tool should we use? So let's suppose, for example, let's say that right. Let's suppose that this happens. Right. Let's suppose that HEAS right, is supported in some ball. Okay. I suppose it's supported in some ball. That's more than what we have, but let's do something like that. Okay. Okay. Well, right. So we're trying to show that these guys converge in L1, right? So that would mean that we're trying to show basically that what are we trying to show? That we can control the size of the difference in L1. Right? That's what we're trying to do. Control, for sufficiently, we can make this, if we, for small enough epsilon 1 and epsilon 2, we can control this difference. Right? Okay. So, do you have an idea? Does anyone have any ideas? Or should I leave this as a homework problem? Maybe this is not a bad one. Okay, well maybe I'll leave this on the problem. Right. This is probably orders of magnitude easier than the current than the usual homework problem. Is that good, or do you want to hear some idea? Luis, do you have an idea?
Maybe like splitting up the integral.
Yeah. In this case, right? In this case, right? Because you know that when you've got this thing, right? You're trying to control this thing, and so you're going to break it into like you're going to break it into the small part, right, and the part like this, and you can make, because of the decay, you can if you choose your given some epsilon, you can make this part as small as you want, right? So basically, you can assume that you're working on a bounded set, right? Okay, and then how do you control the thing on the bounded set? Well, you have the L2 convergence, right? What allows you to get from L1 result? How do you bound the L1 result with an L2 result? By using Hilbert's inequality, or Cauchy-Schwarz. Okay. Okay. So in any case, these guys converge in L1. Is that what you said?
Yeah, I think that's what
Great.
you're going along those lines.
Yeah.
Great. Very good. Yeah. So that I'm pretty sure that will do. Okay. So they converge in L1 to something that we can call the Hilbert transform of F. And that gives you that Hilbert transform of A. So that gives you that this thing in O1 is bounded by some constant. Okay. So so now we've got the stuff. We've got the results that we wanted for the behavior on atoms. Now to deal with general F in H1, we use the atomic decomposition, of course. F is going to be F has an atomic decomposition. Atomic decomposition, and so if we take the Hilbert transform, if we take the truncated Hilbert transforms L1 norm, right? What we get from the this is bounded by some constant. Constant, and so you end up with this being controlled by the constant times the sum of the absolute values of the coefficients. Right, and so taking infimums over all decompositions, we get that HDF in L1 is controlled by the Hilbert space norm of F. So Luis, that's how we define the Hilbert space norm. It's the infimum over all atomic decompositions of the little L1 norm of the coefficients. Yeah.
Is this the same A?
The same name, yeah. Right. 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 This thing converges in L1. You recall that this converges in L1 to F. Right. So you're taking the Hilbert transform of this sum, right? get the sum of the absolute values of this times the A, bounded by A. Okay, so so the last thing to do is to show that so the last thing to do is to show that that these guys converge in L1. Okay, so last bit, last part. We need to show that that these guys converge. And then once they do, that's the end, right? Because that thing will be HF, and we'll have the bound that we want. Okay. See, right now, yeah. So okay, so. So what we do is say, okay, let S of n be the partial sum from k equals 1 to n. Okay. Notice that S of n is itself a multiple of an atom. A multiple of an atom because it's a sum. It's a finite sum. Any finite sum of atoms is a multiple of an atom, right? It will be bound. It will be supported on some ball, right? And it will have integral 0. So you just need to multiply it by the correct number to make its L infinity norm, right? And then that makes it a none. Okay. So this guy is a multiple of an atom. And so, so we know that, we already know that this converges, right? So for fixed n, this thing converges in L1 as epsilon is the same. Okay, so so we can sort of pull that part out, right? So now consider HE1 F minus H epsilon 2F in the L1 norm of that, right? That if we slide in our S of n is going to be controlled by the triangle inequality. HE1 of n plus HE2 of n plus HE1 F minus of n L1 norm plus HE2 F minus of n. Right? Just by the triangle. Okay, and we're being very rough with the triangle. Okay, so because of the convergence, because of this convergence, right? So because of star, we can make this. That gives us control over this thing, right? This thing we can make as small as we want. Right? These guys converge in L1 to the same thing. Okay? So we can make this as small as we want. Okay. Now for this thing, we're going to be a bit more crude about it. remember we got that this is bounded by the H1, okay, by the Hardy space norm of this thing. Okay, that's one here. Right, and so we have two of those things. Okay, but the f sub n, of course, converge to f, right? The f sub n converge to f, and so we can make this f sub n converge to f, and so we have control. We can make this whole thing as small as we want, and that gives it to us, right? So. H does converge in L1 right, to something that we call the Hilbert transform, and as before, we see that the Hilbert transform is then bounded on from H1 to L1. Okay. Okay. So any questions about that? Okay. So second part of today, Hardy space and maximal functions. So we're going to give really what we're going to get is what we'd like to get is a characterization of Hardy space in terms of maximal functions. And the point is the main thing that's going to be different is that that we're not going to that instead of taking the average of the absolute value of the function, we're going to take the absolute values out. And the reason is that if you put the absolute values in, you can't tell the difference between the function. You can't observe the cancellation of the function, right? So the Hardy little maximal function will not be able to recognize if the function is in H1 or not, because it doesn't see cancellation. Okay. So here's the idea. So recall the notion of the approximation of identity. So recall the notion of approximation of So and for us today, we're going to do it like this. Let phi be a compactly bounded, compactly supported function with the integral of phi being 1. Okay. And actually, I'm going to throw in non-negative. That'll make it easier. So then, for f in L1, it's possible to see that when you convolve, let, as usual, phi sub epsilon be the dilation. Let this guy, phi sub epsilon, be the dilation of phi. Right? So it's dilated to the epsilon scale. And you notice that that the L1 norm doesn't change. Right? It always has the same mass. Then it's possible to see, along the argument that we gave before, that this recovers your function AE as epsilon goes to 0. Remember, the intuition is that you're convolving with this thing which starts to look more and more like a Dirac delta, Dirac point mass. Convolving a point mass would theoretically allow you to recover your function. Okay. In the next section, in the next chapter, when we get to distributions, we actually will convolve with the Dirac. We will have a notion of convolution that allows us to convolve with measures. Okay. So starting with this, the approximation of the identity, we're going to create a Maximal function based on phi. So given phi as above, define m sub phi by it's going to be the function. It's going to be the operator that takes your function, and then you convolve that function with phi at the scale epsilon, and take the supremum over all scales of the absolute value of that. So you say we're moving the absolute value to the outside, basically, right? You don't convolve with the absolute value of the function, which is basically what the old maximal function did. But you convolve first, and then you take the absolute value, and this allows you to catch some necessary characteristics. Okay. Let's make an observation that if f is in L1, so what's the relation with the old maximal function? If phi is in L1, then the maximal function is going to be bigger than the absolute value of the function, and bounded above by the some multiple of the party level of maximal function. Okay. And the reason for this latter part is you can argue like this. approximate phi with some as some combination as a step function, where all the a's are positive. As some sort of finite step function. Then, when you convolve with phi, well, of course you're getting this sort of thing, a sub j, f convolved with the characteristic function of some ball, right? Which is bounded by the a is all positive. Do you see this? Convolving with the characteristic function of the ball, right? If I had a 1 over the measure of b, sorry, I should measure of b here. If I convolve with 1 over the measure of b times the characteristic function of b, then that's taking the average of f over that ball. Right? That's taking the average of f over that ball. But that means that so just notice, of course, that if I convolve with this guy at x, right? This is taking the average of f over the ball bj centered at x, right? And so this is controlled by the maximal function, by the Hardy-Littlewood maximal function at x, right? And then you just multiply both sides by bj. So what does that give you? That gives you that, in fact, you get the integral of phi times the maximal function at x. So, right. So, I guess since we assumed the integral of phi was 1, in fact, we can just assume that this constant is 1 here. So the maximal function associated with phi is trapped between the absolute value and the Hardy-Littlewood maximal function. Okay. So right, and then you take you approximate your phi with limits of such sums. So, okay. So the main result here is going to be the following. If your phi is smooth and compactly supported, then n phi is bounded from H1 into L1. with, so that is, the L1 norm, thinking about some H, that so that you get some sort of boundedness condition, and in fact, so remark, it can be shown that that this is actually true from the other from the other side as well. That the L1 norm of the maximal function applied to phi applied to f is actually approximately the same thing as the H1 norm of f. Okay, and so this is the maybe this is another way that one could define Hardy space. You say, I'm going to consider the functions in L1 such that when you hit them with the such that when you take the maximal function of these guys, the L1 norm is still finite. Okay, and we'll call the H1 norm of f the L1 norm of the maximal function applied to f. Okay, so this is that will give you an equivalent definition of Hardy space.
Is there
Yeah.
like one way better than the other, or?
So I think Stein's mode is clear in this case, right? He wrote the book. He is using the atomic decomposition as the definition of Hardy space, and saying, oh, it turns out to be equivalent to this guy. They're all equivalent, so it doesn't you just want to say, which one do I want to use? Right? Whichever way is more useful at the time is the better one. Right? But maybe pedagogically, Stein is thinking that introducing the atomic decomposition is the cleaner way. And I think I agree with it. Yeah. But if you look in the old book, so this book, the blue books were written starting in 2001 and finishing in 2004 or 5, I think. Somewhere there. Yeah, so, and this book is done in the opposite way. That is, he defines H1 using maximal functions, actually something even more involved, something called a grand maximal function, or non-tangential maximal functions. He defines H1 in multiple ways there, and then shows that it has an atomic decomposition. Okay. So So let's see if we can get this. I'm hoping to get to BMO this time, but I'm not sure if we'll make it. I think we might be able to make it. Okay, so let's see if we can get there. So notice that, so first thing to notice is that because of the atomic decomposition, it suffices to show that M phi A, I just use a regular A from now on, it's just too much trouble to make this fancy A, is bounded by some constant. It's bounded by this constant A. Because, in the same way as before, right, because then, for then, if F has an atomic composition, you know that this thing is going to be controlled by A times the sum of the constant. constants, and then you take infimums again, and then you get the result that you want. Infimums, and you're done. Okay. So that's good, right? You notice that this isn't the same thing as proving the result for atoms, right? This is rather proving that the L1 norm of the atom is bounded by some constant. Okay. So so that's the first observation. So notice that because of the decomposition, it suffices to show this sort of thing. Second observation. Also note that M sub phi commutes with dilations and translations. Right, the M applied to a dilation will be the dilation of M applied to the function. And so we may assume that the atom that we're dealing with is supported on a unit ball centered at the origin. And then the proof of the control that we want will basically follow almost the same lines that the proof of the Hilbert transform did. The proof of that the L1 norm of the Hilbert transform, the truncated Hilbert transform applied to an atom is bounded by some constant. It's almost exactly the same proof, or at least the same ideas. So you say, okay, well, so now we don't have, you remember to get the local control, in the Hilbert case of the truncated Hilbert transform, we use the L2 boundedness. Well, we don't have L2 boundedness here, right? Well, we have something pretty straightforward, which is L infinity boundedness, right? If you take a function and then you're taking averages of the function, then you're going to be, right? If you take this thing, which is defined to be the supremum of a convolved with B sub B over all scales, this is controlled by the L infinity norm of this times the L1 norm of your phi. And since we're on a unit ball, this is 1, and we also assume this thing to be 1. So this is 1. This is smaller. Or in general, what we're saying is that this thing is bounded on L infinity. Right? We don't have to have an A here. It's bounded on L infinity. Okay. So, but the point is that for us, if we break, right, we're trying to show that this integral. We're trying to show that this integral is small, right? And so we break it up into the parts x less than 2 and x bigger than 2. Okay. And what we see is that we can make, since the thing is bounded, this thing is bounded by some constant 4 or 2. to the D. Or 4 to the D. So we use the we don't have we have boundedness, we have LP boundedness, and so we use that thing to control the local part. And as before, we'll use cancellation to control the global part. So for x of magnitude bigger than 2, let's consider A involved with dx. So by definition, that is 1 over epsilon to the d. A sub y phi x minus y over epsilon d1. And which you can, using cancellation, we slide in, we see that that's the same thing as this. By cancellation. Okay, so observe, we make a bunch of observations. First is that phi is in C1 and has compact support, so we know that that this is controlled by some constant times the difference in the inputs. Right? In particular, I mean, A is supported on the unit ball, so we know that y is smaller than 1, so this is smaller than C epsilon. Okay. Second thing to observe is that x is bigger than 2, right? And y is smaller than 1. So x minus 1 is bigger than epsilon of x over 2. Third thing to observe is that since phi has compact support, we know that x minus y over epsilon is smaller than, we can assume this is smaller than some constant A. Because outside of there, phi is 0. So what that gives us is that x over 2 epsilon is less than A. From the above, right, we know that we know that this thing over epsilon is smaller than A. And that tells us that so we can assume x over 2 epsilon is less than A. That is to say that epsilon is bigger than x over 2A. So putting this all together, we get that 1 over epsilon to the b times if we look at this term, it's controlled by right. So this is from part 1, and this is from part 2. Part 3. Okay, and so integrating integrating this thing over x bigger than 2 gives us something smaller than some constant. So the global part gets controlled, is controlled. So the global part is integrating, so the 2 parts of the integral are each controlled by some constant that depends on nothing, and so the L1 norm, right? So the L1 norm is this thing. Okay, and so that's it. Okay, so 10 minutes left. That's enough time to start talking about BMO. So I believe BMO first occurred in the context of statistics. And it was only much later that one found out that it was actually the dual of Hardy space. So it was sort of a nice result. And the result is in Stein's book he attributes it to Pfefferman, to Charles Pfefferman, the Fields medalist. But I think people usually refer to it as Pfefferman-Stein duality. So I'm not sure why maybe Stein is just being kind and doesn't want to toot his own horn or something. So he says, oh, this result is due to Charles Pfefferman. But people usually call it Pfefferman-Stein duality. In any case, so let f be a locally integrable function, and let fb denote the mean volume, so the average, right? The average of f over b. Sometimes you'll see people use this notation. They put a slash through it to mean that you divide by the size in the set. If the integral, if you look at the difference of the function from its mean, you look at how the function differs from its mean on the ball, and you take the average. You take the average of that. So the average difference of the function from its mean. Okay. The average of the absolute value of the difference of the function from its mean. Right? If you just, without the absolute values, it's 0. Right? If you look at that over all balls, okay, and that turns out to be finite. So if this is finite, we say F is a bounded mean oscillation. Bounded mean oscillation. In BMO. Okay. And in that case, if the thing is finite, then we call this number in which case we call this supremum the BMO norm. It's also commonly written just F with a little star under it instead of FBMO. Okay, so some comments. One, if F is constant, then it has 0 BMO norm. Okay. So in particular, if you add on a constant, if you have your function and you add on a constant to it, then you're not changing its BMO norm. Okay. So really, in order to make this a norm, you need to take the equivalence classes modulo additive constants. Okay. So one base equivalence classes of functions modulo additive constants. Second observation is that suppose the bound were true for some different constants. C sub B. Suppose that for each ball you can find some constant and call it C sub B, and it turns out that this thing is bounded over all C sub B, that this thing is bounded over all B. In that case, it still implies that F is in BMO, because if you look at FB minus CB, right, that's controlled by suppose there were some bound A. Suppose you change all the constants and you get some bound A here. Okay. Well, it's still going to be in BMO because if you look at the difference between F of B and C sub B, you see that that the difference between f of b and c sub b, f sub b and c sub b is going to be controlled by A. And that would tell you, that implies that the difference between the function and its true norm would be controlled by 2A. So if you manage to get some bound for some arbitrary constants, that gives you some control on the actual DMO norm. A couple of other observations. If f is in DMO, then f sub I of f is in DMO. If f and g are in DMO, then the minimum or the maximum are in DMO. And the last one, which will be useful for us, is that if f is in DMO, then fk, which we define to be k if f exceeds k, negative k if f is less than negative k, and f otherwise. Is also in DMO with DMO norm controlled by DMO norm. So this says that if you have a DMO function, then it's okay to, if you truncate it at a particular height, and you just set it equal to, you say, I'm going to take the minimum between this and k, or the maximum between this and negative k here. You create this new truncated function that these guys have the same DMO norms. And as you see, they converge pointwise to the original function as k goes to infinity. Okay, so I hope to get through at least part of this today, but let me just state what we're going to go for. So next goal is to show that, in fact, the dual of H1 is DMO. So that is, we'll show that given any function g in DMO, then the linear functional LG, defined as integration against g, can be extended to all of H1, and its dual norm will be controlled by some multiple of the DMO norm, some multiple of the DMO norm, and conversely, given any L in H1R star, then there exists a G such that L equals LG. And in that case, the norm of this linear functional is bounded below by some constant times the DMO norm of G. Okay. So that is to say that BMO can be realized in this sense to be the dual space of H1, which is really great. And we'll be able to see that using the atomic decomposition. Okay, and then after that, we'll go into chapter 3, and chapter 3 will start off sort of a lot more basic than what we've been doing, just with definitions of these things called distributions, so-called generalized functions. Okay, that's it.